this seminar. I'm going to discuss some free boundary problem for vector valued function. It is, I discuss the minimizer of such a functional I of u equals integral of d. D is some domain in Rn. Gradient u squared plus modulus of u dx. U is vector valued function. Sometimes I shall write in this way. U1, U, n capital. Okay. In some prescribed boundary data. If we fix boundary data, then minimizer satisfies the system of Euler-Lagrange equations, which has the following form. For each component of U, we have such an equation. UK modulus of U, this vector valued function. So it is singular where U is modulus of U is 0, where U vanishes. Therefore, here I write the characteristic function of set where U is positive. So in domain D, we have some where maybe modulus of U is 0, maybe it is 0 here on some surface. And here we have good equation, this one, and for each component, okay, from 1 to n. So I call this set modulus of U greater than a positive, I denote it by omega of U. It is unknown, and the boundary of this set, d omega of U intersection with our domain, is free boundary. Gamma. This is free boundary. It is unknown. And it may consist of two parts. On some part of free boundary, it may be that gradient of U doesn't vanish. I denoted gamma star. Gamma star is a set where set of gamma, x of gamma, where gradient of U doesn't vanish, positive. And another part is a set x0. I usually write x0 for points of this part, where gradient of U vanishes. And this part is, we can say something about the smoothness of this part, because due to known results about implicit function theorem. But the main problem is to understand what is the smoothness of this part, where U vanishes together with this gradient. This is generalization of classical obstacle problem. If instead of, if we have n equals 1, scalar case, then it will be a solution of the following for n equals 1. U equals signum of U in D. And this is so-called two-phase free boundary problem, and this problem was investigated in our joint papers with Henrik Chagalan and Georg Weiss. There are rather complete results for such scalar problem. If if we consider the scalar case with non-negative boundary values, then solution of this problem is also non-negative, and then we have a classical obstacle problem. If it is well known that it is very important things which we use when study free boundary, smoothness of free boundary and solution for this equation. We use two Montanisti formulas, formula by Weiss and also Alt-Caffarelli-Friedman, Montanisti formula. Now I remind what is Weiss-Montanisti Weiss functional. It is the similar Montanisti formula due to Weiss may be easily obtained for this vector valued case too. So I write what is U, x0, it is point of free boundary usually, and R is positive parameter. It is 1 over R in degree n plus 2. Here, integral over a ball of radius R with the center x0, gradient of U squared plus 2 modulus of U minus 2, and here integral over the boundary of this ball, modulus of U squared. And if we make rescaling U, if we denote by UR of X, U of x0 plus Rx over R squared, then it will be rewritten in terms of these scale functions as integral over unit ball with a center at the origin. I don't sign 0 here. Gradient of UR squared plus 2UR and minus 2. So this is invariant with respect to scaling such a functional. C1 I usually denote it. It is the same as the boundary of unit ball with the center at the origin, UR squared. And what is may be proved similarly as in scalar case, that the derivative of W, this function with respect to R, equals R integral over C1 unit sphere d u r dr squared. So it is non-negative. It is just the same as, maybe here too, I don't remember exactly, r s r, and here dur with respect to normal on the unit sphere minus 2ur squared. And from here it is, we usually, it is standard consideration. We prove that it is monotone increasing with respect to r, this function. And if these scaled functions are uniformly bounded with respect to r, then we have we can go to limit when r goes to 0, and ur goes to some blow up limit u0 at this point x0. And for the limit function, such an expression will be identically 0. And it means that u0 is a homogeneous function of degree 2. For any lambda positive and any x from Rn. It is one monotonicity formula which holds true for vector valued case. This similar proof as in scalar case. Another useful instrument in scalar case is Alt-Caffarelli-Friedman monotonicity formula, which usually we apply to the derivatives, first derivatives of u. And in this case, this nonlinear, in scalar case it is sine of u, it's very good right-hand side, but in vector valued, this expression is not fine, therefore we cannot use Alt-Caffarelli-Friedman. And therefore, problem is non-standard and require another approach compared with scalar case. Now I formulate some results which I give some comments some later. But what is standard? When we make, of course, we hope that we have such a quadratic growth near gamma 0, C distance squared from x to gamma 0. If we have such an estimate, then we can do this rescaling and obtain blow-up limit which is homogeneous. And now it is necessary to understand to say something about blow-up limit. So I shall discuss only the case when x0 is a point one phase free boundary point where x0 belongs to gamma 0, this part. And suppose now that we have such an estimate. Of course, we may expect that free boundary is smooth near this point if after scaling we obtain a solution, we obtain global solution, homogeneous global solution U0, for which free boundary will be the plane. And therefore, I introduce now a special class of global homogeneous solution. It is special class of homogeneous solution. Which has have the following form. I denote such solution usually by h small of x equals, it is vector now, I remind you. So it is some vector, constant vector a, this modulus equals 1. And here, standard function x times nu plus squared half, where nu is unit vector in Rn, some unit vector. It is positive, maybe I write here plus. It is a special solution of this equation, such that if, for example, nu is xn, here h is modulus of h is positive, here it is positive, and here it is identically 0. If nu has such directed along x and axis, if we have a blow-up limit of such form, then we can expect that a free boundary in the neighborhood of this point is smooth enough. Let me denote by R capital the set of so-called regular points of free boundary. It is the set of free boundary points gamma 0, for which is where there exists at least one blow up a blow up limit u at this point at x0, which belongs to this special class, so has such a form. And main result, which I want to explain, is that main theorem is that for each point, regular point, there is a neighborhood where there exists a neighborhood radius of, depending on this point, of course, such that gamma in this neighborhood is a surface is C1 plus beta surface. Beta is depends only on dimension and supremum of modulus of U, which I denoted by M. It is a constant which we assume be given, for example, from boundary data. And to prove this result, what is necessary? The first step, important step, is to characterize the set of regular points in some quantitative way. I formulate the corresponding theorem, theorem 1. Let U be a homogeneous solution. I usually, when I discuss homogeneous solution, I consider it in a unit ball because it may be expanded on the whole space, of course. Then, for this equation, the following is true. For homogeneous solution, this is 0 if all U R coincide with U, of course. Therefore, it is 0. So W doesn't depend on R, and I write only this. I mean it, for example, it is the W of U with the center of origin in origin and ball 1. I may write here arbitrary R, it is the same. Then the first statement is that it is less the great, not less than some constant alpha n, half I denoted, which is measure of unit sphere, n minus dimensional measure of unit sphere over for n plus 2. And this is so it is a minimal value of so because of Montanisty, Weiss-Montanisty formula, we have we can say that for there exists a limit W when R goes to 0 of U x0, 0. If you have quadratic growth estimate, then there exists such a limit, and this limit will be exactly the value of Weiss functional on blow-up limit. But then it means that for each point of gamma 0, we can prescribe some value, and it is bounded from below from this special value. Then the second statement that if for homogeneous solution W equals alpha n is half of alpha n, it means that U is from this special class of half-space solutions. And also, if we consider infimum W over all homogeneous solutions which are not from the special class, then we obtain some constant which is strictly greater than I denoted by alpha n. Wave which is strictly greater than alpha n half. So in a class of homogeneous solution, this we can prescribe, classify global solution in such a way that in this class we have minimal value alpha n half. For any other global solution, we have strictly greater value of Weiss functional. And from here, it is easy to conclude that H is isolated from in W1 1 to norm in B1 from other homogeneous solution. It is this special class is isolated from other global solutions. I will comment the proof of the theorem. This will apply some spectral considerations about spectral properties for the Beltrami-Laplace operator on sphere. And from this theorem, it follows that this special class may be also characterized by the class X0 for which W, this limit U X0 R, when R goes to 0, it exists at each point, and this limit equals alpha n half. So another way to formulate this main theorem is if for any free boundary point where this limit equals this minimal constant, then in some neighborhood of such a point, U is a surface of this class. So there exists a normal vector which is satisfy Hölder condition. Beta is some absolute constant dependent on n maybe and supremum of modulus of U, some positive constant. So unique exponent for any regular free boundary point. And how to prove this theorem? Here we use the approach suggested by Weiss many years ago, more than 10 years ago, when he studied classical obstacle problem. He suggested to apply so-called epiparametric inequality. I don't know what means this term. What does it mean, epiparametric? But it comes from some papers on minimal surfaces. So parameter, minimal parameter, perimeter. Okay. This theorem may be formulated. I formulate what is similar. Here, we don't have, this theorem is not about solutions. It is a theorem concerns functions homogeneous in B1, lambda x equals lambda squared C of x for any lambda greater than 0, x from B1, with the center in the origin. And the theorem says that there exist two positive constants, delta positive, such that if this function, homogeneous function, close to h, distance from C to H is small enough, distance in W12 in B1, then the following is true. I use this Weiss functional. Also, this is not solution. It is arbitrary homogeneous function. But I can calculate Weiss functional on this C. And the theorem says that there exists a function E from W12 in B1 such with the same boundary values as C on D B1 equals this C, for which the value of Weiss functional is estimated in the following way. This W from of C plus upper, and here is a minimum value, our minimal value of Weiss functional on this set of solutions, special set of solutions. And how to use this theorem? If we consider some ball of radius r, and take boundary value of our solution, U, which we want to investigate, and extend it inside this ball of radius r by homogeneous function of degree 2. So CR of x will be our solution, will be homogeneous function. U in x0 is our point under investigation, and here r x over modulus of x. This is a point of no unit sphere, and then we take point on a boundary of a ball of radius r and continue it in a quadratic way inside the ball. Then if we compare this function with our scaled function ur, then ur is minimizer in BR. Therefore, we can say, if there exists some function, then we can write here ur. ur, the scaled function. And then it is a rather general proof, which was is used many times, I think, not only by Weiss, but maybe some people from minimal surfaces, that from such information, here we use minimality of our solution. The theorem says that there exists some function, but then we use our minimizer, and we can write, and from here we can obtain we can say that W of UR with a center of 0, of course, minus alpha n half. We know that for regular point, this goes to 0, it goes to 0. So we can control it. And it's less than some constant r of r0 if it is, if we have for r less than some 0, some value, then we have such an estimate. It follows only from this information, this epiperimetric inequality. And from here, it is also a standard step. It is possible to prove that UR, maybe I write here x0, it is scaling at this point, minus this blow-up limit, which is from H, some special connected with this point, L1 norm of this difference over unit sphere less than CR of R0 in degree beta. And from here, then it is possible to prove that it is possible using what is very important, that if we have for some set we have part of gamma 0, some compact set of regular point. Let K will be a compact set of regular point. The point where we have minimal value of this function. Then for all these points, it is possible to prove that these constants are uniform for all this compact set. And then we obtain that these estimates are also uniform with respect to this compact set of free boundary. And using these uniform estimates, it's possible to prove that if we consider two closed functions, x and y, and let it will be nu. We prove that the nu is this vector characterizing the limit, blow-up limit. It is a normal. It turns out that it is a normal at this point, and there is nu x here and nu x y here, and the difference between them also may be estimated nu x minus nu y less than some absolute constant r in degree beta over 1 plus beta. So Hölder continuity. Okay, I have a little time. So the most involved part of this proof, what really we need to check to prove the main theorem? It is necessary to generalize this epiperimetric inequality to vector valued case. It is most involved part of the proof. The next step, we also to make rescaling and blow-up limits, we need quadratic estimate for solution near gamma 0. It requires some different approach. Here we use the Almgren Montagnesi formula. And also we essentially use this classification of all global solutions. And now let me explain more in more details this part, the classification of global solutions. Because it was strange, but it was one of the most non-standard steps. Because usually classification, in classification, we apply Altcafarelli-Friedman theorem, but not here. It's impossible here. The first lemma concerning homogeneous solution, U is homogeneous solution. What does it mean? It means that U of x may be written in the following homogeneous with respect to the origin, of course. U times V on theta, where theta is a point on the unit sphere R. R is modulus of x. And if we use U is vector for any component, we have this. And if we substitute this in our equations, we will get for Vk the following equation, minus delta prime. This is Beltrami Laplace on sphere. K plus Vk over modulus of V equals 2n. It's due to homogeneity of degree 2 Vk. And this is true in each component omega prime of the set where modulus of U positive intersection with unit sphere. So for any on unit, we can consider any component of our solution, angular part, is a solution of such, it is eigenfunction of operator V is lambda Vk, where L is minus delta prime, Beltrami Laplace, plus some potential, to Schrödinger operator, where Q is 1 over modulus of V. So our potential is inside omega prime is continuous, and it goes to infinity on the boundary. So it is not very standard eigenfunction. And Vk equals, it is in omega prime, and on the boundary of prime it is 0. And it is a good, will be very good situation if 2n will be, would be the first eigenvalue of this operator in this domain. Because in this case, all this Vk would be linearly dependent if it is the first eigenvalue. And if they are linearly dependent, then Vk equals some Ak modulus of V with unit vector A here. And then and correspondingly for U, we have the same. And our system became, reduces to the scalar case, which we know, about which we know all the information. So it was, the task was to prove that under some assumptions, this is the first eigenvalue for in omega prime. And the first lemma will be the following. If we consider, if we know that this component, in some component where Vk is non-zero, suppose that support of Vk, support of Vk, it is our omega prime. A prime contains, is contained in a small neighborhood of a half sphere. And delta is delta neighborhood of a half sphere, S1 plus. I denoted some half sphere. Where delta depends on dimension and on, I suppose that our potential Q not less than some positive constant in omega prime from this Q0, minimal value of potential. Then 2n is the first eigenvalue for this problem. And in this case, all is okay because we have linearly dependent components of V, and all is reduced to scalar case. And we may say why it is true. Now, let me explain why we have such a statement. So we suppose, let's, our omega prime is here. It is not, here u is 0. We know, maybe it is also 0 here. I don't suppose that the boundary of omega prime is in the neighborhood of equator. I don't suppose it. I suppose that all the components, some component is inside some delta neighborhood of half sphere. Then let's consider the second eigenvalue for this operator in this domain. Second eigenvalue. Due to the current minimax principle, we may say that it is not less than mu of f, I write, where mu of f is infimum such an integral, gradient v, gradient, tangential gradient squared, plus q, our potential, v squared, over S1, and minimum, we take minimum over all the following set. I write it's MF. It is a set functions which are with unit L2 norm, which has support V in omega prime, and also which orthogonal to some function f in L2. It is L2 scalar product. So f is arbitrary function from W to 1. Then it is greater than infimum the same integral, the same integral over tangential gradient over S1 over this set, plus infimum of this part, but Q is greater than Q0, and norm, L2 norm is 1. So we can write this. Now, let us choose f in special way. Let f will be the first eigenfunction of the Laplace operator, Laplace Beltrami operator, in with Dirichlet data, of course, in this domain. Let f will be the first eigenfunction for this operator, not L. Then this will be the second eigenvalue of the Laplace Beltrami in omega prime. But because our omega in delta neighborhood of unit sphere, we can write that it is greater than this, greater than minus delta, the second eigenvalue in this S1 plus. And if delta is small enough, And for the second eigenvalue Beltrami Laplace in half sphere is exactly 2n. Therefore, we can write that this value is greater than 2n minus some epsilon of delta, which goes to 0 when delta goes to 0. And due to this, we can write that the second eigenvalue of our operator, which we investigate in omega prime, greater than 2n minus epsilon of delta plus q0. And we see that if delta is small enough, then this will be positive, and therefore lambda 2 is greater than 2n, therefore our 2n will be the first eigenvalue. And thus we can prove this. And from here, from this lemma, what is the lemma? If we have a component which is not far from half sphere, in a neighborhood, delta neighborhood of half sphere, then in fact we have situation when 2n is the first eigenvalue, therefore all our decay are linearly dependent. Now, consider, suppose we have several components of omega, but all of them not far in delta neighborhood of half sphere. If here, the first component, if on the whole boundary of this component u is 0 together with gradient, we can extend u by 0 outside and use the classical result about obstacle problem. If we have some part of free boundary gamma star where gradient doesn't vanish, what we can say here? Because here all the components uk is ak modulus of u here. And here we have, in the next component, we have the same, because it is also in delta neighborhood of half sphere. Therefore, here we have this, and here we have another. And it is also unit vector. And because we know that our information, we know that u is C1, it follows from general theory. Therefore, and gradient is non-zero on this part. This means that bk equals minus ak. And therefore, we can continue, and finally, we will come to the situation, because we know that here it's identical to 0. And we reduce it to the scalar two-phase problem. Okay. And that is all. Thank you.
Any questions or comments? I do have a question. I didn't quite understand the application of the epiparametric inequality. How do you replace V with UR?
UR is a minimizer in B1 with respect to given boundary data.
Okay, right. And so the function is less than. Okay.
Yeah. because they have the same boundary data, the vice function will coincide with our U, I.
That's right. Other questions?
Maybe I missed something. Sorry. So this means that singularities for this problem are more or less the same nature as we have for scalar two-phase problem.
For
Like scalar
scalar.
two-phase.
We, for vector valued case, we studied only the situation, not branch points, but the boundary where after rescaling we have
Yes, okay.
almost this situation. But what is
Yeah.
proof that there exists some.
So you mean that for this calligraphic age, we have the same kind of regularity as we have for scalar one, but branching points are still open.
I cannot say now almost. I can say almost nothing about branch points.
Okay.
But in fact, what may be in vector valued case is that we in one part of omega we have solution of such form, and in another we have with different in general it may be different phase, different AK in one phase, in another BK in another. It is two different phases. We have different phases. In scalar case, we have only two cases, U plus, U positive, and U negative. And here, each component may be different in different phases. So the situation is more complicated.
Anything else? If not, let's thank the speaker again. We start again in 10 minutes.
Okay, before you go,